start the recording here. Okay. Okay, does that look all right? All right. So MRI came along in about the 70s. I think the notion that you could do imaging with magnetic resonance. Initially, nuclear magnetic resonance was used as a tool in chemistry for looking at chemical compounds by taking their NMR spectra. So the systems were available for small samples, but the field gradients that we'll discuss today, which were also available, were used to make the main magnetic field very uniform. And when you scaled this system up to actually put a human inside, it looks something like this, cartoon, where you have it essentially a tube. It's a cylindrical tube. We have windings, coil windings, going around this cylinder with current running through them to make a very large magnetic field. And the magnetic field points essentially in this direction, the tube. There's a patient table, such as with CT, where you can move the patient up and down in this superior inferior direction to position them in the center of the machine. On the inside of the magnetic field windings, we'll see we have these other coils. The current is pulsed through these coils, it's sort of audio frequencies, to modify the main magnetic field as a function of position inside the volume you're imaging. And then inside those gradient coils are radio frequency coils, which are used to irradiate the patient with RF. And these are high power radio frequency antennas that transmit the RF into the patient. And the frequency that transmission occurs for MR scanners, it ranges considerably from, under a megahertz to all the way up to, 400 megahertz. Classic 1.5 Tesla MRI system, which is probably 75% of systems that are deployed in the world. The main magnetic field is 1.5 Tesla, and the frequency at which it operates is about 64 megahertz. Here's a little rogues gallery of all of the high field systems that are available in the world. A 3 Tesla system is pretty well just off the shelf product now from any manufacturer. And there are a fair number of these field now. What is considered still a slightly exotic system, but is available just as a product, is a 7 Tesla system. And each manufacturer makes a 7 Tesla system. And these are used mostly for very high resolution musculoskeletal and high resolution neurological imaging. It's very difficult to image the heart at 7 Tesla for reasons we'll look at. And then there are custom systems that have been built specifically to see what MRI imaging looks like at higher and higher frequencies. And so you see these very large systems. This one, France, one at the NIH, it's almost 12 Tesla. The cost of the system obviously does not go up linearly with Tesla, right? So this system at almost 12 Tesla is probably a lot more than 4 times as expensive as a 3 Tesla system. You can go the other way as well, and that is a number of manufacturers make low field systems, and the advantage there sometimes is that you can make it much more open. So this is essentially a large C here. I think this system actually is a superconducting magnet. So it's a you can look up on this website, but it's interesting that there's a new superconducting material that's used to create the windings in the magnet, and so you can get a half a Tesla between these two poles. There's quite a lot of force at that point, between these two poles that they want to pull together. So you have a very, strong. So basically, you can have it in this orientation where you can gain access to the patient if you're doing some kind of intervention and the patient doesn't feel at all claustrophobic here. And then another way of setting the system up, even this exactly the same system, you rotate it and then the patient can move in and do positioning such that their spine is actually underweight, right? So here, when you're lying down, your spine can be in a different conformation than it can here. And so you can also, if you wanted, you could create a platform here to stand on and look at your knee under force and things like that. So these usually run down at half a Tesla or lower. Many of them are at 0.35 and 0.2 and things like that, these open systems. And then there's this system here called Hyperfine. I don't know, the picture got cut off, sorry about that. But I've given you a link there, you can look it up. It's pretty cool. It's built by a PI at Mass General. And it's a very low field system, 0.06 Tesla. But you just roll it up to the bedside and you can plug it into the wall, right? And then image, a head or a knee or something inside the system. And so it brings MRI to the patient as opposed to having a huge installation in which you have to have the patient come to. Looking at the size of the magnetic field in one of these systems, 1 Tesla equals 10,000 Gauss, and the Earth's field is about half a Gauss. It varies depending where you're standing on the planet, how strong the Earth's field is. But the nominal value is half a Gauss, which is not much. It's 50 microtesla, right? So this magnetic field Tesla is considerable, and probably the greatest hazard with magnetic resonance imaging is not radiation, because it's radio frequency energy. It is flying metallic objects. Because if you bring a ferromagnetic object into the room, it will get pulled into the scanner at a very high velocity. And so all of the fatalities from MRI have been due to people getting pinned against the magnet with an oxygen bottle or an oxygen bottle hitting them when they're in the magnet. So you don't want to bring something like that, a very heavy metallic object, into the scanner, right? I'm sorry, was that a question? Oh, I guess that was random background noise. Yeah, you can if you're talking, you know the shit because probably Professor hit your mute button. That way we won't hear your conversation. So therein lies the risk of MRI, and you just basically, to use one of these machines, you undergo training to try and remind you not to bring stuff like that into the room. So there's a couple of concepts that you need to carry around with you in MRI. And one is basically, it's called the Larmor frequency. And this is the frequency at which protons will absorb and re-emit radio frequency energy as a function of the magnetic field. And when you apply a B field to, so you have a bucket and it's got water in it, the protons will respond to an RF frequency that is at a specific number that is governed by this Larmor frequency. And gamma is the constant that connects the frequency to the magnetic field. So at 1.5 T, the Larmor frequency for protons is about 64 megahertz. and we haven't put gamma on this slide, but you can, its value, you can just compute its value. I think it's 42.58 megahertz per Tesla. And so what does this frequency look like? Well, on your dial in your car, when you're listening to the radio, if you dial into 89.5, that's 89.5 megahertz, that signal is coming out at. The MR scanner down the hall is 64 megahertz.
Oh, the second one?
Pio Blanco, we're hearing you talk. I don't know if it's questions or what, but do you have a question?
No, I don't. I apologize.
Oh, okay. Okay. If you can mute, that'd be great. Thanks. So the way magnetic resonance is modeled, how we model how the signal occurs, is using a concept called the magnetization vector. And this is a way to describe how radio frequency energy is absorbed by a sample. And mostly what we're imaging, you can image different nuclei, but we're mostly going to image protons. And in the body, protons occur mostly in water. They also occur in fat, though, and so you'll see signal from protons in fat. The magnetization vector is a concept such that when you apply a static magnetic field, so we put this sample in that 1.5 T magnet, the sample itself will generate a magnetization vector. It will become slightly magnetized, okay? And this is the difference between the protons that are in the lower energy spin state. So they're a spin 1/2 particle, and they can exist in two states in a magnetic field, spin up or spin down. Spin up, they have a slightly higher energy than the spin down condition. And it turns out that energy is exactly the energy carried by a photon at the Larmor frequency, right? So 64 megahertz photon carries just the amount of energy to flip a spin from the spin down into the spin up configuration. That's how that works. To characterize that difference between the spin up and spin down condition, there are slightly more protons in the spin down state in equilibrium. And so you get what we call a magnetization vector. All of MRI can be modeled by looking at the equations of motion of this magnetization vector. And if you write a simulation about MRI, that's what you're going to do. So here I've shown the magnetization vector both in the Z direction, which is the direction along the magnetic field, and if we tip it away from the Z direction by some angle alpha, its projection into what is called the transverse plane, which is just the plane that is perpendicular to Z. So in the patient coordinates, this would be the axial plane, right? If the patient's lying in the magnet. What happens when you tip that magnetization away from the Z direction is it begins to precess in this transverse plane, right? And that precession occurs at the Larmor frequency, right? So if we have a B field here in the Z direction, and I push my magnetization away from the Z direction, it will begin to precess around the B field. How do we get it at some angle away from the Z direction? Well, we apply an orthogonal B field, orthogonal to the Z direction. Remember, our static field is in the Z direction. And now we're going to apply a magnetic field orthogonal to that. So say along the X axis. And that B field, that magnetic field, B1, is provided by the radio frequency coil. If you pulse the radio frequency coil with an oscillating electric current at 64 megahertz, it will create a magnetic field that essentially rotates around at 64 megahertz. So if we look at the at what's going on with the magnetization vector in the rotating coordinate system, in a coordinate system that rotates at 64 megahertz, what we see is the magnetization vector just processing around this B field and tipping down in such that it has a component in the transverse plane. And this is called the tip angle alpha, right? So if I apply this with a certain amplitude, I get a certain precession rate, keep it on for a given time, and I can create any alpha I like, right? I could even keep that on such that I put the magnetization vector right in the transverse plane. If I keep it on for twice as long as that, I can put it all the way to negative Z. So that's called RF excitation, right? If we had, this is the simplest pulse sequence diagram you can imagine. And what happens here is this gating signal here says my RF is on at a certain amplitude when this is up, and then it's off here. So if I, excuse me, pulse my RF on, the magnetization vector begins to process away from the Z direction. And when I turn the RF off at this time where it goes back down to 0, right here, turn it off, the magnetization vector now has a transverse component, and I see a signal in my receiver coil because that magnetization vector is now precessing in the transverse plane. This FID, it's called the free induction decay, is the envelope of the amplitude of that signal. So inside this envelope, we would have a 64 megahertz oscillation occurring and diminishing in time, okay? In the rotating frame, instead of seeing this oscillating 64 megahertz sine wave with this envelope, we would just see this component, right? That's after transforming to the rotating frame or the 64 megahertz frame. So what does the hardware look like to make this happen? Here's the patient lying in the bore of the scanner. The coil used to transmit the radio frequency to create that B1 field we saw in the previous figure usually looks something like this. It's a set of conducting wires in which the current is phase delayed around each one of these components, and it creates a magnetic field that, say, at one time is pointing out of the patient's chest, but then it rotates it around the patient like this, right? And so at some time later, here the magnetic field is pointing out their back, and then sometime later it's pointing out their side here, and it's just rotating around, right? So that is the transmit coil. You can also use this coil to, once you've stopped transmitting, you turn the coil off, you can connect it then electronically to a bunch of preamps and listen for signal coming back from the patient, because what you will do, the magnetization vector in the patient now has been tipped away from the Z direction, and as it processes in the transverse plane, it will give off radio frequency energy, and you can measure it in this coil. That's not the optimal way to receive the signal because the coil elements are so far away from the patient. So usually you place a separate receiver coil system right on the patient. And so this adds to the claustrophobia of MR, but it's just, part of the business is that you want to get these receiver coils that receive RF energy from the patient as close as possible to the patient, because their sensitivity drops off with distance away from the patient. So if you can put a coil inside the patient, even better. And so people have invented coils that go inside people. So that's how that's done. Here's an example of a receiver coil for doing brain imaging, in which it's a composite of a whole bunch of smaller little rings. And each one of these little rings is a separate coil. It has a field of view in front of it that is fairly local. And so this coil really doesn't care about what's going on in the back of this person's head. This coil will pick that up. This coil really only cares what's going on in the front. And so if you have enough receivers, you can essentially make, you know, if this has 32 receiver channels on it, you can make 32 separate images, each one of the sensitivity of this little of each little coil, and add those up. And that gives you a better sensitivity, right? Better signal to noise, because the coils are more local to the signal that they're receiving. The next type of coil we'll look at is the gradient coils. And the gradient coil changes the magnetic field as a function of position inside the imaging volume, okay? So we have this blue element here, which is our radio frequency transceiver coil. And then outside it, one layer outside it, we have 3 sets of gradient coils. And these are what they look like idealistically, you know, as a cartoon. This is what they look like when they're built in the shop, okay? And you can see the copper strip here, that's where the current will run in this gradient coil. It'll run, each one of these strips will have current running through it. It looks like these are called thumbprint coils for, you know, obvious reasons. They look like a fingerprint or a thumbprint. And this exact pathway has been generated through computer modeling of the current to generate a change in the magnetic field inside the volume that is the most uniform, right, with respect to one coordinate. Those gradient coils, you know, these strips of wire here that have current pulsed in them, have actually a lot of current pulsed in them. They are ramped up to very high current values, and in order to make them get to a high current value in a hurry, so you don't want to spend too long ramping up the current, you want it to get to its value quickly, you have to use a very high watt amplifier, right, that have high voltage, high watts. And so analogic now builds about, I don't know, 75% or something of all the amplifiers for this application in the world. And these are really beefy amplifiers. They put out now a megawatt of power, right? Nobody's an audiophile anymore, but when I was in high school, you know, if you had like a 250 watt amplifier, you were pretty cool, and it made really great sound. But we're talking a megawatt here, and in the Metallica 2017 World Tour, they used 367 kilowatts. So take that, Lars. We got a lot more power, and this cabinet lives pretty close to the magnet. It's like within a few meters away, and behind some door, right? And you pulse these currents, it turns out, at roughly audio frequencies. So they get turned off and on, these currents, at what looks like audio frequencies. So in the early days of MR, these were just off-the-shelf audio amplifiers. So let's look at the gradient coils in a bit more detail. And so we have 3 sets: a Z coil, a Y coil, X coil. And let's see how the Z coil functions first. If I'm sitting here inside the bore and I have a 1.5 Tesla magnetic field at this point, and it's pretty uniform, say across this whole volume here, it's 1.5 Tesla. If I put a current in a coil right here that's rotating in this direction, right? Using the right-hand rule, if I put my fingers around the coil in this direction, I know that I'm going to produce more magnetic field in this direction. So at this point, my magnetic field will be 1.5 Tesla plus whatever contribution I get from this coil that's pulsed. In this coil, instead of pulsing in this direction to produce an increase in the field, we'll pulse the current in the opposite direction, this way. And that gives me a delta magnetic field, or a change in the magnetic field that goes in this direction. So in the negative Z direction. So while those two coils are pulsing, one in this direction, one in this direction, I will get a linear gradient of magnetic field across the sample in the Z direction. I'll still be at 1.5 Tesla right between the two coils, and I'll grow in field strength to a max when I'm inside this coil and decrease to a min when I'm inside this coil, and then they'll roll back to their ground value. So that produces a linear magnetic field gradient. Now, it's important to know, even though X and Y coils are going to make linear field gradients in the Z magnetic field, okay? It's easiest to understand in the Z coil. We'll look at X and Y in a minute. So with this knowledge that we can make a linear magnetic field gradient across the sample, we can also immediately, very simply, make a volume selective radio frequency pulse. So instead of just, when I irradiate the sample at 64 megahertz, saying I have this gradient on, right? So that really the only protons that are susceptible to the 64 megahertz excitations are the protons that are in the central plane, right? Because they are the ones that remain at 1.5 Tesla. The protons over here are below that. The protons here are above that. So there's one plane of photons in here that are at 64 megahertz. So if I can essentially limit my frequency bandwidth of my RF to 64 megahertz plus or minus some very small number, I will get a thin selected plane of protons that will be excited by this RF pulse. And the way that excitation is done is you modulate your radio frequency pulse with a sync function. And that sync function has a specific width that after Fourier transformation is a specific frequency width, right? So this is a sync function that has its first two zero crossings, 2 milliseconds width. This sync function, the Fourier transform of this, is 1 kilohertz wide, right? And so the 64 megahertz radiation that is inside this envelope, right, will be seen, basically, it will have a bandwidth of 1 kilohertz, okay? So if we show how this works with a pulse sequence diagram, what happens is, this is a pulse sequence diagram. We're going to see more and more complex versions of this. This is time in this direction. And this is amplitude of the Z gradient. This is amplitude of the RF and this received signal, or the free induction decay. So we'll switch on our Z gradient. We'll produce 64 megahertz RF inside an envelope that modulates like this, right? We'll then shut the gradient off, the Z gradient off. And what we now have is a 1 kilohertz wide slab of our sample that when the gradient was on, it's 1 kilohertz wide. When the gradient's off, now everything's at 1.5 T, but I still have this slab that frequency corresponds to a certain linear dimension in space. One thing that happens inside that slab is, from one side to the other of the slab, there is a phase shift across it. And so we usually use a negative gradient to rephase the spins in that slice. So we rephase them here. And then at this point, from the front of the slice to the back of the slice, all of the protons are in phase and they start giving us a large signal. And that signal decays away with a time constant called T2. If everything's perfect, it's called T2 star if there's magnetic field, residual magnetic field gradients from other things. Okay, let me just check the time here. So, okay. As we saw with that diagram of the tip angle, if the magnetic field, the static magnetic field, which is B0, these are common notations. So we start at time 0 with a magnetization that is in equilibrium, doesn't change with time, it's M0. If we give a small pulse, small amplitude pulse, we can tip the magnetization away a small tip angle and generate a signal from this transverse magnetization that begins to precess. And that gives us a small amount of signal. If I push my amplitude of the RF such that alpha now equals 90 degrees, so I rotate the magnetization all the way into the transverse plane, this now gives me the maximum signal possible after a single RF pulse. That's called a 90-degree RF pulse. And we won't talk about refocusing pulses right now, but a 180-degree inversion pulse, you can imagine, is just twice the amplitude of this one or twice the duration, and the magnetization goes to -Z. At this point, when you turn off your RF and you listen for a signal, you will not see one, right? Because there's nothing in the transverse plane. The magnetization vector is not there. There's no projection in the transverse plane. So this magnetization will just slowly go back to its equilibrium value, right? Without giving off any signal. And there will be a time when if you made an image at some delay after producing this pulse, so you delay until the magnetization is right at 0. When you make your image, whatever tissue has the magnetization here at 0 will turn up as with 0 signal. It'll just be black in the image. All right. So to review, what the gradient does is it changes the Z component of the magnetic field as a function of position in the magnet. We looked before at changing the frequency as a function of Z along the patient. Now we'll look at changing it as a function of X. You can imagine that if immediately after performing my RF pulse, I turn on an X gradient, then if this is the, say, the left side of the patient, protons on the left side of the patient will be processing at a higher frequency than protons on the right side of the patient, right? And so I can, through this process, encode their position along that direction by acquiring signal while this gradient is on, right? So the center of my imaging device is kind of defined by where this gradient has a 0 delta BZ. That defines the center line, and then anything on this side is going at progressively higher frequencies. Anything on this side is going at progressively lower frequencies, depending on how far in X you are displaced from that center. And here's how that gets accomplished with a X gradient coil. These are called Golay coils. We saw from the factory picture, they don't have this idealized simple geometry. They look like a thumbprint, but the principle is basically the same. So if we're above the patient looking down and say their head is here and their feet is here and their left arm is over here and their right arm is over here, how do I make a change in the Z B field with this X gradient coil? Well, with this geometry of windings, if I put my current in this direction, here, using the right-hand rule again, if I put my thumb along this direction on my right hand, that is the direction of the B field that will be created by that current. So the Z component of the B field right here will get bigger when this is pulsed this way. So it'll go this way. And if I have a complementary coil on the other side, but I don't, excuse me, I gotta take a break. I'm gonna. Okay. So now I pulse current in this coil in this direction. And I use the same right-hand rule. I can increase the Z field at this position. So for X increasing, I have increased the Z field. And if I do the mirror image of those currents over here, I decrease the B field for the parts of the patient that are on the left, right? And ideally, this is a linear, this is just a straight line, this change in field, right? Obviously, it's not perfect. Trying to make it a straight line is why they have those sophisticated printed current distributions. So now we'll stop here because this is a good stopping point, but we're at a point where we can look at the effect of reading out a signal while a gradient is on. So here is my object, right? And this is straight out of that little, 20-page write-up for the Introduction to MRI for Engineers that's in the modules section. So you can go back and read the text in that if this isn't clear. But this is a simple object, right, in the plane, and this is the X direction. I apply a slice selective pulse, right, refocus the slice, and I get a signal. If I take a Fourier transform of that signal, I get a single peak. All of the protons in all of these samples are processing, or all of the magnetization vectors are processing at the same frequency, at the Larmor frequency. I don't have any gradient on to make them process at different frequencies. And so they all add up to give me this signal, and I get Fourier transform, I get one peak, right? And it's at that frequency. On the other hand, if I change my pulse sequence such that during my acquisition of the signal, I turn on this X gradient with those Golay coils, then along this direction, right, the magnetization vectors will process at progressively higher frequencies the farther I go in this direction. So I have now columns of my sample that are processing at a specific X determined frequency, right, because of the X gradient. And so a column here is processing at a lower frequency than a column over here. And so when I turn the gradient on, measure my signal, I now take the Fourier transform of that signal to break up the composition of frequencies. When I look at it on the frequency axis, it looks like this, right? So we look at this sample, and look at that sample. Okay, well, what is this? And that's the big question. And this was the aha moment, I think, in the 70s that occurred when people had NMR spectrometers. I think people that had struggled shimming their field and got themselves into a position where they had a large gradient across the sample, looked at their spectrum and said, hey, wait a minute. This is my sample and this is what I get. This is a projection of that sample onto this axis, right? So now, immediately, if you think back to CT, we know we can make an image, right? Because if you can make a projection through the sample, you can make an image. And so we could just change the direction of this X gradient into a different direction and make another projection in that direction, like this. And that's how the first MR images were done by Paul Audibert, who eventually won the Nobel Prize for this technology. on his spectrometer, right? And it was a very simple image of like 2 or 3 test tubes, and by changing the direction of this gradient and then doing back projection, he made a picture. Okay, I'm running out of voice, so what I will do